Okay, welcome back to Unit 10. In this unit we talked about thermochemistry first, and in this recording, which is the third recording in the set, we will be talking about equilibrium. In chemical systems, the forward and reverse reaction are occurring at the same time. They often are, and products combine to form reactants as reactants combine to form products. The concentrations of these species is a ratio called the equilibrium expression. In this section, we'll be discussing the factors that affect that equilibrium. The processes are manipulated to help make more products or make the reaction occur more efficiently. And so this is an important part of chemistry and a somewhat advanced concept. And so in this discussion of equilibrium, we'll be talking about the principles mainly, and we'll hold off on doing the mathematical part because really I think the concepts are really more important than the math. So let's get started. Okay, so when we talk about chemical equilibrium, we say it's a dynamic equilibrium because products and reactants are constantly being formed after the reaction starts. And so when you mix your reactants up, they automatically form the products, and as soon as that happens, the products reform to make the reactants. And so this forward and reverse reaction are happening at the same rate. So the system in a dynamic equilibrium is when the rate of the forward and the reverse reactions occur at the same rate. So in our example here, we have carbon monoxide and hydrogen forming methane and water. And so as soon as those are mixed up in a container in a closed space, the methane and the water react to form the carbon monoxide and hydrogen. So this happens almost instantaneously, and you can do things to predict how fast these things will occur, and that's the study of kinetics. In this discussion of equilibrium, we'll be more concerned with the concentrations of the reactants and the products than we will the rate in which it occurs. And so when we talk about these concentrations, we write what we call a equilibrium expression. And in this equilibrium expression, Kc, you take the concentrations of the products raised to their coefficients and multiply them together, and then that is divided by the concentration of the reactants raised to their coefficients, and you get a number here. It's important to note that these are molar concentrations, or moles per liter of those species. So it says here the equilibrium constant expression Kc is obtained by multiplying the concentrations of the products raised to their coefficients divided by the concentrations of the reactants raised to their coefficients. So it's always products divided by reactants. And so we'll talk more in depth about this in a minute. But if you have a Kc value that is a lot greater than 1, it favors products. If it's a lot less than 1, it favors reactants. You can also write these in terms of the partial pressures of gases involved in a reaction. And so we see here our example of the pressure of methane times the pressure of water, the partial pressures of those species, divided by the pressure of the reactants, which is carbon monoxide and hydrogen. So again here, it is products divided by reactants, but instead of molar concentrations, we talk about the partial pressures of those gases in the mix. Okay, so there we go. The partial pressures are used. Okay, so now we're going to compare what we call a homogeneous equilibrium to a heterogeneous equilibrium. Homogeneous equilibriums involve a single phase. Like in our last example, all the phases were gas phases, right? Everything, all the reactants and products were in the gaseous state. And so that would be an example of a homogeneous equilibrium. We have another example here of mixing nitrogen gas and hydrogen gas to form ammonia. So that would be an example of a homogeneous equilibrium because they're all in the gaseous state. The Kc for that, again, can be written a couple different ways. It can be written as the molar concentration of ammonia to its coefficient squared, right, divided by the concentration of nitrogen gas times the concentration of hydrogen gas raised to its coefficient, which is a 3 there. So that's how you would write the Kc value. Since these are gases, it could also be partial pressures as well. It could be the partial pressure of ammonia raised to the second divided by the partial pressure of nitrogen times the partial pressure of hydrogen raised to its coefficient. If the value of Kc is large, the mixture is mostly products. If it is small, the mixture is mostly reactants. If the value is around 1, the equilibrium contains appreciable amounts of both reactants and products. So they're close to being the same amount of each if the coefficient is close to 1. So in heterogeneous equilibrium, it involves reactants and products in more than one phase. In these types, you omit concentrations of pure solids and liquids in the concentration expression. So an example here is one where we have iron and water in the gaseous state. The products here are iron oxide, it would be iron 3 oxide, and hydrogen. And so the only things that will appear in the equilibrium expression are things that are not pure, that are the gaseous states here. Here we have solids that will not be included in the expression. It's important to note here that even though they're not in the equilibrium expression, they have to be present for the reaction to occur. So, but they maintain their concentrations, and their concentrations don't change, and so the concentrations of the water and the hydrogen are the most important. So here our Kc value is our concentration of our product hydrogen raised to the 4th, and our concentration of water raised to the 4th power. The equilibrium concentration is not affected by iron and iron oxide just as long as some of each is present during this reaction. Okay, so now we're going to talk about something called LeChatelier's principle. So when a system reaches equilibrium, it wants to maintain that equilibrium. So if it is disturbed by a change of temperature, pressure, or concentration, the shift in equilibrium compensates in a way that counteracts the change. All right, so in our first example here, when more reactant is added or some product is removed, more product is produced to reestablish the equilibrium. So let's do a little example here and talk about that. So let's say that we have some hydrogen gas and some oxygen gas mixed together to form our gaseous water. All right, let's balance the equation here just so that we're in good shape. So we'll have to put a 2 next to the water and a 2 next to the H2. And so now we are balanced. And so let's say that we, so it says here, so when more reactant is added, okay, so that's our first example here. So we're going to add more hydrogen. We're going to add some hydrogen gas to the system. The reaction will shift from the left to the right. So here's the left part of our reaction, and here's the right part. So it's going to shift in this direction to produce more water, so that the ratio of water to hydrogen and oxygen maintains the same ratio. And then it says, or some product is removed. So if we remove the product, if we remove the water, if we take that out, then you're going to produce more hydrogen and oxygen to produce that water. So it's still going to shift from the left to the right to maintain that ratio of hydrogen and oxygen to water. Of course, the water in our equilibrium expression will be written on the top. So if we were to write Kc for this thing, you'd have the concentration of water raised to the second power, right, over the concentration of hydrogen raised to the second power to the concentration of oxygen. All right. So more product is added or some reactant is removed, more reactants are produced to reestablish the equilibrium, and the equilibrium shifts from right to left. So if the other is true in our example here, so if we remove the hydrogen, then the reaction is going to shift this way to make more hydrogen to reestablish the equilibrium. So if more product is added or some reactant is removed, more reactants are needed. So in this case, let's say that we add more product, the reaction is going to shift in from right to left also. So it says here, if the reactant is removed or more product is made, the reaction shifts to the left, like so. All right. Although the concentration of reactants and products may change, the value of Kc will eventually return to its original value. Thus, the term dynamic equilibrium. It's changing, but it also seeks to maintain the same ratios. LeChatelier's principle, changing concentrations and pressures. Okay, it says predict the direction of a reaction when H2 is removed from a mixture in the following equation. Okay, so let's predict that for a second. So if we remove H2, what's going to happen to the reaction? It's going to shift towards H2 to produce more of it, so the ratio remains the same. So we get a shift to the left. The reaction will increase direction to move so more HI will dissolve to replace the H2 and the I2 to partially restore the H2 that was removed. Pressure changes. When the pressure is increased, the equilibrium concentrations will change to alleviate the effects. The concentration will shift toward the direction with a fewer number of moles to reduce the pressure. Okay, and here's our example. So here, if we increase the pressure, it increases the effect of the carbon monoxide because it has the most moles. So to alleviate that pressure, the system shifts to the left to alleviate that pressure and produce more of the carbon dioxide. Increasing the pressure causes a shift to the reverse direction, and of course in this case we ignore the solids involved. In an endothermic reaction, the amounts of products are increased at equilibrium by an increase in temperature. Kc is larger at higher temperatures. Notice here that the actual value of Kc will change. And then it says for an exothermic reaction, the amounts of products are increased at equilibrium by a decrease in temperature. Kc is larger at low temperatures. Okay, and we're going to do a couple of examples of this so you can see why that is. Note that this is the only effect that changes Kc. And so some examples here. All right, so here we have carbon monoxide and hydrogen forming methane and water. And we have a negative value for our enthalpy exchange. And that should be in kilojoules here per mole. And so this is an exothermic reaction. So it's an exothermic reaction. So when I look at this, I kind of look at it as the energy being on the heat being on the product side of the reaction. And so It says here, for an exothermic reaction, the amount of products is increased at equilibrium by a decrease in temperature. So if you decrease the temperature here, it's going to shift away from the, it's going to shift toward the heat that's being lost. So here in an exothermic reaction, if you decrease the heat here, the reaction is going to shift towards the product side to make it more, to replace the energy that is lost. So for an exothermic reaction, the amount of products are increased at equilibrium by a decrease in temperature. So here you can think of the energy being on this side, and if you lose that energy, the system is going to shift toward that side to replace that energy that's lost, and so the products will increase. So Kc is larger at low temperatures. Increasing the temperature will shift the reaction to make more reactants, thus lowering the value of Kc. So here, if we increase the temperature, here, right, the reaction shifts to make more reactants because you're increasing that, so it's going to shift in the opposite direction to get away from that change in energy. And so in that case, we make more reactants. And so Kc goes, in this case, Kc goes down, lowers the value of Kc. Okay, LeChatelier's principle, increasing the temperature would shift the reaction to form more products and increase the Kc value. So here we have a endothermic reaction, right? When you don't see a sign, it's assumed to be positive. So in this case, you can think of the energy being on the product side. So here you have the heat here on this side of the reaction. So increasing the temperature, okay, increasing the temperature here is going to shift it away from that temperature, and so it's going to form more products and therefore increase the value of Kc. Remember, when we write Kc here, it's always going to be the products over the reactants. Okay, and of course here I almost wrote the carbon down, but remember we ignore the solid in the equilibrium expression. So since we're shifting toward the products, Kc is going to go up. All right, and so of course the reverse would be true there as well. If you decrease the temperature, it would shift toward the reactant side and Kc would go down. A catalyst is a substance that increases the rate of a reaction, but it's not consumed by it. So Kc is not affected, but it would reach Kc quicker with the input of a catalyst. A catalyst has no effect on the equilibrium concentration of a reaction mixture. It just speeds the process towards equilibrium. Okay, some summaries. A summary of the two topics in Unit 10 here. First, let's start with thermodynamics, which we covered in the first two recordings. In those recordings, we talked about the first law of thermodynamics. We said that energy is neither gained or destroyed, but can change form. And we talked about the quantities of heat and work. We said that that in any chemical system, the system has the ability to do work or move an object over a distance, and it also had the property of heat. And we said that some of the energy involved in those systems is lost to heat. We said that chemical reactions can either be exothermic or endothermic. And we said that if the reactions are exothermic, we gave them a designation of Q is equal to a negative value, or delta H is equal to a negative value, which means that the heat is leaving the system into the surroundings. And so in those types of systems, the energy that is created when the bonds formed are greater than the energy required to break the bonds. And then we had endothermic systems whereby the energy required to break the bonds is more than the energy released when the bonds are reformed on the product side. And so we talked about those having a Q value that is positive because the system is absorbing energy, or a delta H value where the system is absorbing energy, so that is positive also. And we talked about the difference between Q and H. We said that delta H is called enthalpy, which is the heat at release or absorbed at constant pressure. And we said Q little p is equal to delta H. Fun. Okay, so let's talk about some of the basic concepts in equilibrium. We said that equilibrium is a dynamic system. That's when you mix the chemicals up, they form products, and as soon as the products are formed, they reform to form reactants in this reversible type of reaction. And we said that the equilibrium is established when the forward and the reverse reactions occur at the same rate. Increasing or decreasing the pressure and the concentrations of the reactants and products stress the equilibrium but do not change it. Increasing or decreasing the temperature can cause a change in the equilibrium expression. And in this we talked about that the equilibrium wants to be maintained, and when we stress the system by increasing the amount of reactants or the amount of products, or we increase the pressure, if there's a difference in the number of moles, the reaction shifts to alleviate that pressure, and we call that LeChatelier's principle. And then we also said that in the equilibrium expression, pure solids and liquids do not enter into the expression itself. And so those are some of the big bullet points from each one of the units. I hope you've enjoyed our discussion of thermodynamics and equilibrium, and hopefully it'll whet your appetite to learn more about these complex interactions in chemistry. So this ends our Unit 10. I've really enjoyed talking about these concepts with you. Do your practice work and do the practice exam and see how you come on those. Look at anything that you are struggling with, replay the slides, and maybe do some additional reading. It's been wonderful. I've really enjoyed being your proctor, I always say, because I don't really think that people learn from just being taught, but maybe they can be inspired, and maybe they can look at something a little bit differently, and hopefully I've piqued your curiosity about these chemical topics and have been a valuable asset to you. Take care. Peace. We'll see you on the flip side.